In this video, we'll demonstrate how to use the techniques of problem solving to solve a type of kinematics problem called a pursuit and capture problem. The problem reads, a gazelle is running at a speed of 48 miles per hour when it passes by a hiding cheetah. The cheetah immediately begins to chase the gazelle. The cheetah can accelerate from rest to 60 miles per hour in a stunning 2.9 seconds. The gazelle is running as fast as it can. And we're asked a number of questions about this situation. What is the gazelle's speed in meters per second? What is the cheetah's acceleration? How long does it take the cheetah to catch the gazelle with constant acceleration? How fast is the cheetah traveling when it catches the gazelle? And how many meters long was the chase? All right, so we're going to follow the standard problem-solving procedure here for kinematics problems. And the first step is always to read the problem and figure out what the problem is trying to tell you. The situation is a little more complex this time because we have two things to keep track of. We have to keep track of the information for the cheetah and for the gazelle. So we must create two data tables now for the cheetah and the gazelle. As before, we note that there are always going to be 6 variables for any kinematics problem: initial and final position, initial and final velocity, acceleration, and time. In this case, however, we have to keep track of separately the quantities for the cheetah and the gazelle. And so I'm going to add another subscript to these so that we can keep the data for the cheetah and the data for the gazelle separately. It's very important that we do this because we cannot mix the data. Notice I have not put a subscript by the time because the time will be the same for both of them. So now we look at the problem and we figure out what the problem is trying to tell us. The first thing the problem tells us is that they both start at the same place. The cheetah immediately begins to chase the gazelle, and so they have the same starting position, which is 0. We are told the initial velocity of the gazelle, 48 miles per hour. However, we're given that in miles per hour, and so we're asked first to convert that into meters per second. So this is a simple exercise in unit conversion where the initial velocity of the gazelle is 48 miles per hour. We go through our unit conversion procedure where there are 1,609 meters in 1 mile, and 1 hour is 3,600 seconds. This will cause the miles to cancel and the hours to cancel, leaving us with meters per second, and that gives us an initial velocity for the gazelle of 21.4 meters per second. That's more significant figures than we need, because this has 2 significant figures in the problem, but we'll retain that extra significant figure for intermediate calculations. We would report this, however, as 21 meters per second. Now this is going to be the same as the final velocity for the gazelle, because we're told the gazelle is running as fast as it can. This means the gazelle has an acceleration of 0. So that's the information we're given about the gazelle. The information we're given about the cheetah, aside from its initial position, is information that we can use to calculate its acceleration, because we are told the cheetah can go from rest to 60 miles per hour in 2.9 seconds. So we can use the definition of acceleration to calculate the acceleration of the cheetah. We have previously calculated that 60 miles per hour is 26.8 meters per second. And the initial velocity, of course, was 0. And that the cheetah accomplishes this acceleration in 2.9 seconds. So to calculate the acceleration, we focus only on these data right here, which tell us the cheetah can go from rest to 60 miles per hour in 2.9 seconds. We convert 60 miles per hour into meters per second, and we calculate the acceleration of the cheetah as being an amazing 9.25 meters per second squared. Cheetahs are capable of incredible accelerations. So that is what we put in for the acceleration of the cheetah. We also know that the cheetah starts from rest, and so it has an initial velocity of 0. So that summarizes everything that we are told by the problem. The second step is to figure out what the problem is asking for. We've already answered the first two questions in the process of getting our data into the right units. And so we are asked, how long does it take the cheetah to catch the gazelle? That is, over here in our data table, that is time. We're asked, how fast is the cheetah traveling when it catches the gazelle? That is, the cheetah's final velocity. And how many meters long was the chase? Well, that can be given by the cheetah's final position. So we have identified the things which the question is asking us for. One thing we need to realize when addressing a pursuit and capture problem is that when the cheetah catches the gazelle, their final positions will agree. That is the condition of the cheetah catching the gazelle. And so, if we can create a situation where their final positions will agree, we can simulate the end of the chase. And this will help us answer the first question, finding the time. Step 3 in this problem-solving process is to look to see what quantities are irrelevant to the problem. And for this first problem, all we're asked for is the time, and so these two variables, final position and final velocity, can be considered to be irrelevant. So if we can find an expression for the final position that does not depend on final velocity, we can solve the problem. Well, that just happens to be one of our kinematics equations, saying that the final position, for example, of the cheetah is going to be the cheetah's initial position plus the initial velocity of the cheetah times the time plus 1/2 times the acceleration of the cheetah times time squared. We can create a similar equation for the gazelle with the gazelle's initial position, the gazelle's initial velocity, and the gazelle's acceleration. Now, these equations become simple very quickly because so many of these quantities are 0. That leaves us with very simplified equations, saying that the final position of the cheetah is 1/2 times the cheetah's acceleration times the time squared, and the final position of the gazelle is the initial velocity of the gazelle times the time. We then set these two equal to each other, and we should be able to solve for the time. So 1/2 times the acceleration of the gazelle times time squared equals the initial velocity of the gazelle times time. So 1/2 times the acceleration of the cheetah times time squared equals the initial velocity of the gazelle times the time. One of those t factors will cancel. And we can then solve the equation for t, getting a total time for the chase of 4.63 seconds. Now, since this problem has two significant figures, we would report this time as 4.6 seconds. So it takes 4.6 seconds for the cheetah to run the gazelle down. Now, this is at constant acceleration, which probably wouldn't happen. The cheetah would probably instinctively get up to a very high speed and then wait for the gazelle to get tired. But this is the amount of time it would take if the cheetah is constantly accelerating. It will very likely take a little bit longer for the hunting cheetah to catch the gazelle. The next question asks us, how fast is the cheetah traveling when it catches the gazelle? That's to find the final velocity of the cheetah. Well, that is, since we know so many other things now, that is a simple matter of using the first kinematics equation to calculate the final velocity. Notice again, I'm still using those subscripts, so I keep the cheetah's data separate from the gazelle's. The initial velocity of the cheetah is 0. The cheetah's acceleration is 9.25 meters per second squared, and the time of the chase is 4.63 seconds. This gives a final velocity for the cheetah of 42.8 meters per second, which is a very high velocity, around 90 miles per hour. Again, not realistic, but this is at constant acceleration. Again, the cheetah would probably get to a more reasonable speed and just wait for the gazelle to get tired. But at constant acceleration, this is the speed the cheetah would reach. Finally, we are asked, how long does the chase take? That is finding either the final position of the cheetah or the final position of the gazelle, since both should be the same. Let's calculate it both ways. The final position of the cheetah is the initial position of the cheetah plus the cheetah's initial velocity times the time plus 1/2 times the acceleration of the cheetah times time squared. Again, the initial position is 0, the initial velocity is 0, and we're left with that. So the final position of the cheetah is 1/2 times 9.25 times 4.63 squared, and that comes out to be 99 meters. We can do likewise to calculate the final position of the gazelle by taking the initial position of the gazelle plus the initial velocity of the gazelle times time plus 1/2 times the acceleration of the gazelle times time squared. Again, the equation is simplified when realizing that so many of the quantities are 0, and so the final position of the gazelle comes down to taking 21.4 and multiplying by 4.63. And this, once again, gives us a result to two significant figures of 99 meters. So, the two final positions agree, and the chase took approximately 99 meters. Again, in reality, the chase would probably have lasted longer, but this is the distance with constant acceleration.